Hello, dear learners. Welcome to week 7 in this course. I am thrilled to guide you through this recorded lecture. And today we are going to cover techniques for predictive modeling. So get ready to expand your knowledge. What do you think predictive modeling is? Let's have a look at what predictive modeling is for marketing companies.
What is predictive modeling? Predictive modeling is used by marketers to take the trial and error out of their marketing campaigns by predicting which actions and strategies are more likely to succeed. It is a process that forecasts outcomes by pairing historical data with analytical algorithms. When businesses use software to track marketing efforts, such as calls, clicks, web leads, and more, they collect data. This data is plugged into a model that takes into account various elements of a marketing campaign, such as demographics, time, and location. Marketers then have the opportunity to adjust different variables, like when and where they are running their ads. Based on these adjustments, the software generates predictive outcomes, allowing marketers to see how campaign changes can impact their marketing outcomes. Predictive modeling gives marketers an advantage by forecasting data-driven outcomes, exposing blind spots, and highlighting potential revenue streams, so marketers can feel confident about their latest campaign strategy. For more information about how predictive modeling can work for you, contact the experts at Phonexa today.
So basically what the video says is that predictive modeling is a tool to look into the past to predict the future. Predictive modeling is the core function in predictive analytics. It is a mathematical process that aims to predict future events or outcomes based on past behaviors. This mathematical process analyzes historical data with the goal of identifying trends or patterns and then using those insights to predict future outcomes. In this lecture, we are going to study the internal structures, capabilities, and limitations and applications of the most popular predictive modeling techniques. They are artificial neural networks and support vector machines. Just a note here that sometimes the terms predictive analytics and predictive modeling are used interchangeably, However, predictive modeling can be understood as the hands-on part of analytical applications. Okay, and as we will see in this lecture, predictive modeling techniques can be implemented in a wide range of problem areas of fields, from online advertising and in marketing to understanding and enhancing efficiency of production process to improving healthcare and medicine. Let's now look at artificial neural networks, ANN. In simple terms, ANN, also known as neural networks, are methods in artificial intelligence that teach computers to process data in a way that is inspired by the human brain. So neural networks are biologically inspired rather than an exact replica of how the brain actually works. So keep that in mind. Neural networks can learn and model. They are super cool because they can learn and model the relationship between inputs and outputs. They are nonlinear and complex. They can also make generalization and inferences and reveal hidden relationships, patterns, and predictions. So those are just some of the things that artificial neural networks can do. Neural networks have been used in many business applications to support different activities, different tasks. For example, neural networks are used in the detection of credit card and Medicare card fraud, and also in the improvement of retail customer experience. And I can explain a little bit about those examples. In credit card and Medicare card fraud detection, banks and credit card companies, they use data from the client's past account usage and employ predictive modeling to detect anomalies. For instance, a credit card that has always been used here in Australia, within Australia, is suddenly used in Brazil. And financial predictive models would alert the credit card owner since his or her account might have been compromised. So it was an unusual activity, and those models will detect that. In the other example, in the improvement of retail customer experience, retail companies, they use transactional data to, for example, track the best days to schedule sales promotion, which products need promotion, and where to position certain products. Walmart, for example, has a patent that allows them to track shoppers' journeys down the grocery aisles. And data from this technology enables Walmart to categorize shoppers and predict their movement and purchases. So just those are just some of the examples of how neural networks have been used. Now I want us to have a look at biological neural networks, the networks that are in our brains, so that we can understand what ANNs are composed of. A biological neural network in our brains, is a network of neurons that are connected by axon and dendrites. So we can see an axon here and the dendrites here. Each network contains several thousand highly interconnected neurons, and so the brain can be viewed as a collection of neural networks, so a bunch of neural networks together. The brain has anywhere between from 50 billion to 150 billion neurons. Here in this slide, we can see an example of two neurons together, two interconnected neurons, the brain cells neurons. The neuron, we say that the neuron is the building block of neural networks. And it is a cell just like any other cell of the body, in our bodies, which has a DNA code, and it is generated in the same way as the other cells of our bodies. A neuron is composed of 3 parts: the cell body, called soma, the dendrites, and the axon. The axon is this long fiber that transports the input or output signal as an electric impulse along its length. And the dendrites are the fibers. They are like fibers branched in different directions and are connected to many cells. The dendrites and axon, they enable the neuron to communicate with its neighboring neurons by transmitting and receiving electrical and chemical signals. At the ending terminal of the axon, the contact with the dendrites is made through synapse. A synapse is able to increase or decrease the strength of the connection between two neurons, and it causes excitation or inhibition of a subsequent neuron. This is how information is transported, is stored in the neural networks. And once the excitation potential is reached, the neuron activates or the neuron fires. And how this information processing works in artificial neural networks. Artificial neural ANNs can be considered as weighted directed graphs where the neurons could be compared to the nodes and the connection between two neurons as weighted edges. So here this slide we can see an illustration of this process. Each artificial neuron receives one or more input signals, and they are represented as numerical values. Each input is multiplied by a corresponding weight value. These weights, they represent the importance of each input. The weighted sum is calculated by adding the products of the inputs and their corresponding weights. So here we can see the weighted sum. The weighted sum is passed through the activation function, here shown as transfer function. The activation function determines the output of the neuron based on the calculated sum. This function also introduces non-linearity into the neuron's response. So this is the output into the response. And this allows the network to learn complex patterns and relationships in the data. And we will talk about this activation transformation function later on in this lecture. The output of the activation function of this function becomes the output of the artificial network. It is this output is either fed into other neurons or is or is used to make prediction or decisions. So it's either fed to other neurons as input or it is used to make predictions or decisions. Okay, so this is the first time you're coming across this slide. We know now that human beings, we cannot pay attention for extended period of time. So what I usually do in my lectures is to include a slide such as this one, so students know when they should take a break, when they can have a rest. So every time you see this slide in my recorded lectures, it means that you should pause the video and have a break. So you can call a friend, call your family, have a cup of water, have a cup of tea. You could also mindlessly scroll through a social media platform, do whatever you have to do to rest a little bit, and then come back to learn more cool stuff when you feel refreshed. So every time you see this slide throughout my recorded lectures, you should make a pause. Okay, welcome back. So now let's see if you have learned something. There are some elements of artificial neural networks that we need to understand even further. They are the processing element of artificial neural networks, the network architecture, and network processing information. The processing elements of an artificial neural network are artificial neurons. As I showed you some slides ago, these artificial neurons, they receive the information from other neurons, perform a transformation on the inputs, and then pass on the transformed information to other neurons or external outputs through the synapse. Regarding the network architecture, ANNs typically consist of multiple layers of interconnected artificial neurons. These layers, they can be broadly categorized into three types: the input layer, hidden layers, and output layer. Here in this slide, we can see the structure of artificial neural network with a single hidden layer. So we've got the input layer, the hidden layer, and the output layer. The hidden layers, we can say that the hidden layers are the intermediate layers between the input layer and the output layer. The hidden layer converts inputs into a nonlinear combination and passes the transformed inputs to the output layer. A neural network can have one or more hidden layers, and the number of neurons in each hidden layer can vary depending on the complexity of the problem being solved. Okay, so let's go back one slide. And I need to talk about parallel processing. It's just a simple thing that you should know. In a neural network, processing of information is performed in parallel. So this means that when information is processed, many of the processing elements of the neural networks or the neurons, they perform their computation at the same time. So this means that information is processed in parallel. Parallel processing is similar to the way a brain works and differs from the serial processing of conventional computing. Another element of an artificial neural network that I've mentioned before and I said I will talk about this later and now is the time, is the activation transformation transfer function. As I mentioned before, the activation transformation function takes the weighted sum of inputs and produces an output or also an activation level. This function determines the threshold at which the neuron is activated. And this function it affects the performance of the network. It affects the network's operation. So you might be thinking, what activation function, what transformation function are used? A popular activation function is the sigmoid function, which maps the weighted sum to a value between 0 and 1. And this function has a S-shaped curve and is widely used in binary classification tasks. So let me show you how this function works by using an example. Okay, so here in this slide, we see a single neuron, and this neuron receives 3 inputs. Those inputs are represented by numerical values, and each input has an importance, has a weight. When we multiply the input by its weight and then sum all of those products, we calculate the summation function, right? And this is what we did here. And then we use the transfer function to map this summation function to a value between 0 and 1. And the value is 0.77. So the output here is equals to 0.77. Other functions that are also used as transformation functions are commonly used as transformation functions in neural networks are the linear function and the tangent hyperbolic function. One thing that I just thought that might not be clear is that we refer to the transformation function as sometimes as an activation function, because sometimes a threshold value is used instead of a transformation function. And the threshold activation function is simply a function that outputs a specific value, for example, 0 or 1, depending on whether the weighted sum of the neuron's inputs exceeds a certain threshold value. So the threshold value represents the minimum required level of activation for the neuron to produce an output, to be activated, to be fired. Let's move now to neural networks architectures. Several NNN paradigms have been proposed for application in many problem areas, in many problem domains. And one easy, simple way to differentiate among them is through the way they process information, and also through how they learn to perform their designated tasks. How information is processed by a neural network is inherently a function of its structure. One popular approach is the so-called feed-forward backpropagation paradigm. Now let's watch this video. Let's have a look to see at this video to understand what feed-forward backpropagation is.
Last summer, my family and I visited Russia. Even though none of us could read Russian, we did not have any trouble in figuring our way out, all thanks to Google's real-time translation of Russian boards into English. This is just one of the several applications of neural networks. Neural networks form the base of deep learning, a subfield of machine learning where the algorithms are inspired by the structure of the human brain. Neural networks take in data, train themselves to recognize the patterns in this data, and then predict the outputs for a new set of similar data. Let's understand how this is done. Let's construct a neural network that differentiates between a square, circle, and triangle. Neural networks are made up of layers of neurons. These neurons are the core processing units of the network. First, we have the input layer, which receives the input. The output layer predicts our final output. In between exist the hidden layers which perform most of the computations required by our network. Here's an image of a circle. This image is composed of 28 by 28 pixels, which make up for 784 pixels. Each pixel is fed as input to each neuron of the first layer. Neurons of one layer are connected to neurons of the next layer through channels. Each of these channels is assigned a numerical value known as weight. The inputs are multiplied to the corresponding weights, and their sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, which is then added to the input sum. This value is then passed through a threshold function called the activation function. The result of the activation function determines if the particular neuron will get activated or not. An activated neuron transmits data to the neurons of the next layer over the channels. In this manner, the data is propagated through the network. This is called forward propagation. In the output layer, the neuron with the highest value fires and determines the output. The values are basically a probability. For example, here, our neuron associated with square has the highest probability. Hence, that's the output predicted by the neural network. Of course, just by a look at it, we know our neural network has made a wrong prediction. But how does the network figure this out? Note that our network is yet to be trained. During this training process, along with the input, our network also has the output fed to it. The predicted output is compared against the actual output to realize the error in prediction. The magnitude of the error indicates how wrong we are, and the sign suggests if our predicted values are higher or lower than expected. The arrows here give an indication of the direction and magnitude of change to reduce the error. This information is then transferred backward through our network. This is known as backpropagation. Now, based on this information, the weights are adjusted. This cycle of forward propagation and backpropagation is iteratively performed with multiple inputs. This process continues until our weights are assigned such that the network can predict the shapes correctly in most of the cases. This brings our training process to an end. You might wonder how long this training process takes. Honestly, neural networks may take hours or even months to train. But time is a reasonable trade-off when compared to its scope. Let us look at some of the prime applications of neural networks. Facial recognition. Cameras on smartphones these days can estimate the age of the person based on their facial features. This is neural networks at play, first differentiating the face from the background, and then correlating the lines and spots on your face to a possible age. Forecasting. Neural networks are trained to understand the patterns and detect the possibility of rainfall or a rise in stock prices with high accuracy. Music composition. Neural networks can even learn patterns in music and train itself enough to compose a fresh tune.
So as the video says, in a feed-forward backpropagation network architecture, the information flows unidirectly from input layer to hidden layer or hidden layers to the output layer and in the opposite direction. The figure in this slide shows an example of feed-forward backpropagation network architecture. And here in this case, we've got survey data on a sample of the population. And information in this data includes whether the person voted yes or no to legalizing gaming. It also shows the social demographic, religious, financial, and other types of background for each respondent. And then using those data, say that we want to predict whether a person voted yes or no to legalizing gaming. And we can define inputs, and we can define weights for those inputs, so the importance of each input in the prediction of this outcome. And as the video shows, those weights, they will be assessed, they will be updated based on the error, so the predicted value versus the actual value. So this, we are using a data in which we know this combination, the social demographic combination of the inputs and the outputs, and in this way this neural network learns and improves its prediction. So learns by mistakes and then improves the predicted outcome. Unlike feed-forward neural networks, where information flows in only one direction, another neural networks paradigm called recurrent neural networks, RNNs, those networks, this paradigm has feedback connections that allow them to retain information about previous inputs and make use of context and temporal dependencies. So as you can see here, there is information going from input layer to the hidden layer, from output layer to the input layer, the hidden layer to the input layer, and so on and so forth. So the connections between the layers and neurons are not unidirectional. So this figure illustrates an R and N, and here we can see that there are many connections in every direction between the layers and neurons, which creates a complex connection structure. Now you know the drill. You should pause the video now and have a rest. I will hopefully see you again in a few minutes. Okay, welcome back. So now it's time for a quiz because we need to check if you've learned something. So give it a try. Now, let's understand the development process of an artificial neural network. This process typically involves 9 key steps. While the specifics of those steps can vary depending based on the problem and the problem's requirements, in this slide here we can see a general outline of the process. One thing that you should note is that the development process of a neural network is not always linear as shown here in this slide. And it can involve many iterations between steps to refine and improve the model's performance. Okay, so let's have a quick, let me give you a quick explanation of each of those steps. So in step 1, we gather the relevant data for training and testing the network. Here in this step, we pre-process the data by cleaning, normalizing, and transforming it into a suitable format for the neural network we are developing. In step 2, we divide the available data into training, validation, and testing sets. The training set, as its name suggests, is used to train the network. The validation set is used to tune the hyperparameters and monitor performance during training, and the testing set is used to evaluate the final performance of the trained network. In step 3, we determine the architecture of the neural network, including the number of layers, types of layers, so fully connected, recurrent, etc., and the number of neurons in each layer of the network. In step 4, we select the learning algorithm. The learning algorithm in a neural network refers to the method or algorithm used to train the network and adjust its weight based on the training data. So the learning method determines how the network learns from the input-output patterns and improves its ability to make accurate predictions or classifications. The most common learning network algorithm, used in neural networks is called backpropagation. So the method we covered in a couple of slides ago. In step 5 and 6, first we initialize the network weights and parameters. Then we experiment with different values for optimizing the performance of the network. Here, we use the validation set to evaluate and compare different configurations. In step 7 and 8, we evaluate the performance of the network on the testing set once the training is completed to assess its generalization capabilities. Here, metrics, here in these steps, metrics such as accuracy should be used. Finally, in the last step, in step 9, we deploy the training neural network in a real world setting, and we monitor its performance over time. Here, new input will be presented to the network, and its output will be a recommended decision. It's important to, when using neural networks for many problems, it is important to continuously collect new data and periodically retrain or update the network to adapt to evolving patterns and changes in the problem domain. Because as we know, we live in a world, everything is changing every time, and we have to keep that in mind when deploying neural networks. As I just mentioned, for the development of a neural networks, we have to divide the available data set into 3 sets: one for training, one for validation, and one for testing. What I want you to know is that the training data set should contain the largest portion of the available data, typically around 60 to 80% of the available data set. On the other hand, the validation and testing sets, each one of them usually accounts for about 10 to 20% of the data set. And in addition to traditional test sets, what is also common to do is to use cross-validation techniques such as the k-fold cross-validation to further assess the network's performance. And cross-validation, this process involves, those techniques involve splitting the data, the available label data, into multiple subsets for training and testing the network interactively. And those techniques are relevant when dealing with limited data, because those techniques, cross-validation techniques, are employed to maximize data utilization and provide a more robust evaluation of the neural network's performance. Cross-validation techniques also reduce the risk of overfitting during testing. I'm most sure that you have heard of overfitting. So I want to know what overfitting is. Shall we understand one cross-validation technique? Yes, we shall. We are gonna learn now the bits and pieces of k-fold cross-validation. This technique is, as I mentioned before, is used to evaluate the performance of models by partitioning the available data set into k equally sized subsets, or also called folds. We can summarize the k-fold cross-validation process in the following way. So first, we divide the data set into k subsets of equal size, and as I mentioned, each subset is referred to as fold. Then the model is trained and evaluated k times. In each iteration, one fold is used as the testing set, and the remaining k minus 1 folds are used as the training set. The experimentation, so this process is repeated for k times, and we compute performance metrics such as accuracy for each time, in each time. Finally, in the last step, the performance metrics obtained from each iteration are averaged out to get an overall assessment of the model's performance. So it's very straightforward. This technique, k-fold cross-validation technique, is very straightforward. Let's jump right into the learning process in artificial networks. In neural networks, there are different types of learning that can be adopted, can be employed based on the nature of the problem and the availability of labeled data. The different types of learning available are supervised learning, unsupervised learning, and reinforcement learning. As I know you must all be tired of my voice, I got someone to explain these three learning approaches to you. So let's have a listen.
Supervised and unsupervised learning are two core components in building machine learning models. So, what's it? Supervised and unsupervised learning are two core components in building machine learning models. So, what's the difference? Well, just to cut to the chase, supervised learning, that uses labeled input and output data, while an unsupervised learning model doesn't. But what does that really mean? Well, let's better define both learning models, go deeper into the differences between them, and then answer the question of which is best for you. Now, in supervised learning, the machine learning algorithm is trained on a labeled data set. So this means that each example in the training data set, the algorithm knows what the correct output is. And the algorithm uses this knowledge to try to generalize to new examples that it's never seen before. Now, using labeled inputs and outputs, the model can measure its accuracy and learn over time. Supervised learning can be actually divided into a couple of subcategories. Firstly, there is a category of classification. And classification talks about where the output is a discrete class label, such as spam and not spam. Linear classifiers support vector machines, or SVMs, decision trees, and random forests. They're all common examples of classification algorithms. The other example is regression. The output here is a continuous value, such as price or probability. Linear regression and logistic regression are two common types of regression algorithms. Now, unsupervised learning is where the machine learning algorithm is not really given any labels at all. And these algorithms discover hidden patterns in data without the need for human intervention. They're unsupervised. Unsupervised learning models are used for three main tasks. There's clustering, association, and dimensionality reduction. So let's take a look at each one of those, starting with clustering. Now, clustering is where the algorithm groups similar experiences together. So a common application of clustering is customer segmentation, where businesses might group customers together based on similarities like, age or location or spending habits, something like that. Then you have association. And association is where the algorithm looks for relationships between variables in the data. Now, association rules are often used in market basket analysis, where businesses want to know which items are often bought together. Something along the lines of customers who bought this item also bought, that sort of thing. The final one to talk about is dimensional dimensional reduction. And this is where the algorithm reduces the number of variables in the data while still preserving as much of the information as possible. Now, often this technique is used in the pre-processing data stage, such as when autoencoders remove noise from visual images to improve picture quality. Okay, so let's talk about the differences between these two types of learning. And in supervised learning, the algorithm learns from training data sets by iteratively making predictions on the data and then adjusting for the correct answer. While supervised learning models tend to be more accurate than unsupervised learning models, they do require all of this upfront human intervention to label the data appropriately. For example, a supervised learning model can predict how long your commute will be on the time of day and thinking about the weather conditions and so forth. But first you'll have to train it to know things like rainy weather extends the driving time. By contrast, unsupervised learning models work on their own to discover the inherent structure of unlabeled data. These models don't need humans to intervene. They can automatically find patterns in data and group them together. So for example, an unsupervised learning model can cluster images by the objects they contain, things like people and animals and buildings, without being told what those objects were ahead of time. Now, an important distinction to make is that unsupervised learning models don't make predictions. They only group data together. So if you were to use an unsupervised learning model on that same commute data set, it would group together commutes with similar conditions like the time of day and the weather, but it wouldn't be able to predict how long each commute would take. Okay, so which of these two options is right for you? In general, supervised learning is more commonly used than unsupervised learning, and that's really because it's more accurate and efficient. But that being said, unsupervised learning has its own advantages. There's two that I can think of. Firstly, unsupervised learning can be used on data that is not labeled, which is often the case in real-world data sets. And then secondly, unsupervised learning can be used to find hidden patterns in data that supervised learning models just wouldn't find. Classifying big data can be a real challenge in supervised learning, but the results are highly accurate and trustworthy. And in contrast, unsupervised learning can handle large volumes of data in real time. But there's a lack of transparency into how that data is clustered and a higher risk of inaccurate results. But wait, it is not an either or choice. May I present to you the middle ground known as semi-supervised learning. This is, well, a happy medium where you use a training data set with both labeled and unlabeled data. And it's particularly useful when it's difficult to extract relevant features from data and when you have a high volume of data. So, for example, you could use a semi-supervised learning algorithm on a data set with millions of images where only a few thousand of those images are actually labeled. Semi-supervised learning is ideal for medical images where a small amount of training data can lead to a significant improvement in accuracy. For example, a radiologist can look at and label some small subset of CT scans for tumors or diseases, and then the machine can more accurately predict which patients might require more medical attention without going through it and labeling the entire set. Machine learning models are a powerful way to gain the data insights that improve our world. The right model for your data depends on the type of data that you have and what you want to do with it. And the choice between supervised and unsupervised learning is only the first step.
What the video doesn't explain is reinforcement learning. And reinforcement learning, in a few words, is the closest learning type to how humans learn. In reinforcement learning, the algorithm learns by interacting with its environment and getting a positive or negative reward. This is what you need to know about reinforcement learning. Let's have a look at supervised learning. Let's have a look at understand the details of supervised learning, because it is one of the most common type of learning in the most adopt learning type of learning in neural networks. In this as the previous video says, this learning type is used in tasks such as classification, regression, and sequence generation. Supervised learning involves training the network using labeled data, where the inputs are paired with their corresponding desired outputs. Supervised learning includes mainly 3 steps: compute temporary outputs, compute outputs with desired targets, and adjust the weights and repeat the process. During the training, the network learns to approximate the mapping between the inputs and outputs by adjusting its weights. And the objective here is to minimize the discrepancy between the predicted outcomes and the desired outcomes, which are the errors, usually called delta. And we calculate those errors using a loss function. Time to rest up. Pause the video here and come back in some minutes. All right, now that you have rested a little bit, let's check your knowledge. Still on supervised learning, I mentioned that supervised learning is the most adopted type of learning in neural networks, and backpropagation is the most widely used supervised learning algorithm in neural computing. That's why in this lecture we are going to learn a little bit about the backpropagation algorithm as a supervised learning method. Recall that using backpropagation, the error is distributed back through the network, providing each neuron in the network with a measure of its contribution to the total error. Using these measures, the backpropagation algorithm adjusts the weights of the network to minimize the error. So this is what backpropagation does. The 6 steps in the backpropagation learning algorithm are displayed in this slide. So we have to initialize weights with random values and set and decide on other network parameters. Then the model reads in the inputs and the desired outcomes. In the 3rd step, it computes the actual output by working forward through the layers of the neural network. Then it computes the error, so the difference between the actual and desired output, and then changes the weights by working backward through the hidden layers. And this process is repeated from reading the inputs and the desired outputs until the weights is stabilized. The figure displayed in this slide is an illustration of the backpropagation of error for a single neuron. So as I mentioned before in the previous slide, the error calculated which is the difference between the actual output and the desired output, is propagated backwards and distributed through the inputs. The goal in the backpropagation algorithm is to improve the accuracy of the network's output during subsequent forward propagation. This is actually a process of optimization, and when it's often employed a technique known as the gradient descendant method. We are not going to learn this method here in this course. Recall that the goal of this course is not to learn the nuts and bolts of all the techniques we cover in this course, but rather to understand what is possible, what is available, what has been done. Artificial neural networks are typically thought of as black boxes. They surely have been proved to be capable of solving complex problems. The problem is there is a lack in the explanation of their capabilities. So those networks do what they do? As you can tell from the previous slides, they are not complicated, but there are many details, important details about them. The problem is, and the thing is, that in some problems there exists a need to know what the network is doing. And in this context, different techniques have been applied to analyze and evaluate trained neural networks. These techniques, they provide a clear, simple interpretation of how a neural network does what it does. And sensitivity analysis is one of these techniques. Do you know what sensitivity analysis is? Have you ever heard about it? Let's check your knowledge. In neural networks, sensitivity analysis helps understand the relative importance or the influence of different features of the model's predictions. There are few approaches to conducting sensitivity analysis in neural networks, and one of them is input perturbation. So this figure shows how this approach, input perturbation, works for sensitivity analysis works. This method involves systematically varying the inputs of the neural network while observing the corresponding changes in the inputs when we do that. This process is repeated for each input in the neural networks. By measuring how sensitive the model predictions are to changes to variations in the specific input variables, we can assess the relative importance of those variables for the model performance, for the performance of the model. All right, let's wrap artificial neural networks up by looking at one of the most commonly known problems in neural networks, which is the classification problem. I want you to have a look at this. When I click on the link in that slide, and I encourage you to do that, to check for yourself, it directs me to this page, and I'm gonna click on this browser demo here, on this demo here, classify C510 with convolutional neural network. And what this page shows is how the training models parameters are changing during the training, and it also shows the layers of this deep learning model. And we've got the input layer, and all the hidden layers are also shown, and we also see the output of this model during the testing phase. And for example, here the dog, it predicted correctly that this image was a dog. So you can go back and have a look at the other examples too. Let's move on to support vector machines, SVMs. SVMs are one of the popular machine learning techniques for classification and regression tasks. SVMs have gained popularity due to many reasons. Among them are their ability to handle high dimensional data, their robustness against overfitting, and their versatility in handling both linear and non-linear problems. SVMs have been successfully applied in different areas, in various domains, including image recognition, text classification, bioinformatics, and finance. And SVMs are among the supervised learning methods that produce input-output functions from a set of labeled data. Because of their architectural similarities, support vector machines are also closely associated with artificial neural networks. In support vector machines, the main objective is to find an optimal hyperplane that best separates the different classes in the input data. And in case you're wondering, a hyperplane is a decision boundary that separates the data points of one class from another. The optimal hyperplane is the one that maximizes the margin, and the margin is the distance between the hyperplane and the closest data points of each class. The data points, those data points that are closest to the hyperplane and directly affect its position are called support vectors. So the question we want to answer here is, what is the hyperplane that best separates the data? What is the classifier hyperplane that is the optimal here? SVMs can only produce linear boundaries between classes by default, which is not suitable for most machine learning applications, because data in real world is cannot be separated, because most data sets in the real world cannot be separated by a hyperplane. However, there is a workaround this, which is in fact, this workaround is in fact the most interesting feature of support vector machines. And it is that support vector machines can even work with a nonlinear data set. But for this, we have to use a trick which is called kernel trick, which makes it easier to classify the points when using support vector machines. Suppose we have a data set like this one. So is you can see the data points plotted in on this graph. Here we see that we cannot draw a single line or say a hyperplane which can classify the points correctly, can classify the points into two sets. So what we do is try converting this lower dimension space to a higher dimension space using the kernel trick. We convert this lower dimension space to a higher dimension space using some quadratic functions, which will allow us to find a decision boundary that clearly divides the data points. And here you can see what the kernel functions do with that data set. And then when points reach this format, we can easily find a single line, a hyperplane that separates the data points into two sets. Let's recap all of what you've learned about support vector machines.
In machine learning, one of the most fundamental tasks is when you have a bunch of objects that you want to classify into two categories or more. Is this picture of a dog or a cat? Is this dog going up or down? SVMs, or support vector machines, are some of the simplest and arguably the most elegant methods for classification. Each object you want to classify is represented as a point in an n-dimensional space, and the coordinates of this point are usually called features. SVMs perform the classification task by drawing a hyperplane, that is, a line in 2D or a plane in 3D, in such a way that all points of one category are on one side of the hyperplane and all points of the other category are on the other side. And while there could be multiple such hyperplanes, SVM tries to find the one that best separates the two categories, in the sense that it maximizes the distance to points in either category. This distance is called the margin, and the points that fall exactly on the margin are called the supporting vectors. To find this hyperplane in the first place, SVM requires a training set, or a set of points that are already labeled with the correct category. This is why SVM is said to be a supervised learning algorithm. In the background, SVM solves a convex optimization problem that maximizes this margin, and where the constraints say that points of each category should be on the correct side of the hyperplane. In practice, you don't have to worry about the implementation details of this optimization problem. Using SVM can be as simple as loading a Python library, preparing your training data, feeding it to the fit function, and calling predict to assign the correct category to a new object. The biggest pros of SVMs is that they are easy to understand, implement, use, and interpret. Furthermore, they are effective when the size of the training data is small. The simplicity of SVMs can also be a problem. In many applications, the points cannot be separated by hyperplane. A common workaround in this case is to A. Augment the data with some nonlinear features that are computed from the existing ones, B. Find the separating hyperplane in this higher dimensional space, and C. Project back to the original space. A clever technique known as the kernel trick allows us to perform all of these steps in a very efficient manner. And now that you know about SVMs, you can use them for face detection, spam filtering, and text recognition. This was SVM in about 2 minutes. Like and subscribe if you like the video, and see you next time.
And how is the process of building using a support vector machine? The process includes mainly 3 stages, 3 steps. And we can see in this slide an illustration of this process. In the first step, data preparation, first we scrub and then we transform the data. Scrubbing the data means that we clean the data. We identify and handle missing, incorrect, and noise data. Then we transform the data into vectors. The input data is represented as a set of feature vectors where each one of the vectors corresponds to a data instance, and each instance is labeled with a class, with a category. Then in step 2, the next step in this process is to develop the model. And for that, we need to first select the kernel type. And we do that based on the data that we've got. Once the kernel is selected, then we need to determine the kernel parameters for this specific selected kernel type. If the results are satisfactory for these selected kernel parameters, then we finalize the model. We've got the model. Otherwise, we have to change the kernel type and the kernel parameters and test the model again. And we do that until we achieve the desired level of accuracy. The last step of this process is the deployment of the model. Once we obtain the quote-unquote optimal support vector machine prediction model, then it means we found a kernel type and kernel parameters, the best kernel type and kernel parameters. Then the next step is to integrate the support vector machine prediction model into the decision support system. Pause, catch a break, and I will see you soon. All right, welcome back, and now let's do a quiz. The two predictive modeling techniques we have covered so far, artificial neural networks and support vector machines, are supervised methods, which means they need labeled data to train on. Apart from this drawback, needing labeled data, these techniques also tend to be highly mathematically and computationally intensive. They involve time-demanding, computationally intensive, interactive mathematical derivations. And so we are now going to learn a simpler predictive classification technique, which is called the k-nearest neighbor algorithm, KNN. But before we do that, before we understand this method, I'd like to recap one thing from last week. I'd like us to recap the k-means clustering algorithm. Who remembers what the k-means clustering algorithm is? So before I recap this, I would like to pose you a question. So do you know what the k-means clustering algorithm is? The k-means clustering algorithm is a popular unsupervised machine learning algorithm used to partition a given data set into groups, into clusters. So data that have similarities, data that are similar to each other, are classified into clusters, into groups. The goal of this method is to assign each data point to one of the k clusters in such a way that the within cluster variance is minimized. The within cluster variance is also known as the sum of square distance between each data point and its assigned centroid. This algorithm, the k-means clustering algorithm, is usually applied to data with a small number of dimensions, data that is numeric and is continuous. This slide shows some of the applications of this algorithm, of the k-means clustering algorithm, and I included links to those applications, so links to examples of those applications, and I encourage you to pause the video here and click on those links to have a look at them, the examples. And just so you know, I don't like cricket, but I found this as an example and I wanted to show to you because I bet there are many cricket lovers in this course. How does the k-means clustering algorithm work? This method works by iteratively assigning data points to clusters and then updating the clusters' centroids until convergence. So we've got mainly 5 steps. So in the first step, we choose the number of clusters k, and we also randomly initialize the cluster centroids. Each centroid represents the center of a cluster. Then in step 2, for each data point, we calculate the distance to each centroid using a distance metric. And it could be, for instance, the Euclidean distance. Then we assign each data point to the cluster with the nearest centroid. Then in the next step, we recalculate the centroids of the clusters by taking the mean of all data points assigned to each cluster. And so in this step, what we are doing is adjusting the position of the centroids. Then we have to repeat step 2 and 3 until convergence. And convergence occurs when the centroids no longer change significantly or a maximum number of iterations is reached. So these two can be the stopping criteria. The last step is when the algorithm outputs the final set of K clusters. And in this case, each data point is assigned to, this happens when each data point is assigned to has been assigned to a specific cluster. Again, the K-means clustering algorithm is a popular unsupervised clustering machine learning algorithm, whereas the K-nearest neighbor method, KNN, which we are going to cover now, is a supervised algorithm. And let's have a look at the K-nearest neighbor algorithm now then. The KNN is among the simplest of all machine learning algorithms, and it is a prediction model for classification, usually used for classification and regression type prediction problems. KNN is a type of instance-based learning where all computations are deferred until the actual prediction. That's why it's a simple method. In this method, K, the letter A, represents the number of neighbors used, which will impact the prediction. I wanted to share with you a video about the KNN method, which I found very interesting, very helpful.
K-nearest neighbor is a super simple supervised machine learning algorithm that can be solved for both classification and regression problem. Here is a simple two-dimensional example for you to have a better understanding of this algorithm. Let's say we want to classify the given point into one of the three groups. In order to find the k-nearest neighbors of the given point, we need to calculate the distance between the given point to the other points. There are many distance functions, but Euclidean is the most commonly used one. Then we need to sort the nearest neighbors of the given point by the distances in increasing order. For the classification problem, the point is classified by a vote of its neighbors. Then the point is assigned to the class most common among its k-nearest neighbors. K-value here controls the balance between overfitting and underfitting. The best value can be found with cross-validation and the learning curve. A small k-value usually leads to low bias but high variance, and a large k usually leads to high bias but low variance. It is important to find a balance between them. For the regression problem, we simply return the average of the k-nearest neighbors labels as the prediction. Here it is a simple code example. We use the very famous ARIES dataset and only take the first two features for demonstration purpose. The k-nearest neighbor algorithm is from sklearn, and it is self-explanatory. I encourage you to try it yourself with different parameters. These two plots are real visualization from the previous code example with different k setting. The left plot shows the classification decision boundary with k equal to 15, and the right plot is for k equal to 3. Thanks for watching. This is bite-size ML concept from Intuitive Machine Learning. If you like this video and want to learn more, make sure to comment, like, and subscribe to our channel. See you at the next one.
As the video says, in the classification type prediction, a case is classified by a majority vote of its neighbors, with the object data point being assigned to the class most common among its nearest neighbors. And when using K and N, there are two critical decisions we have to make. A, to determine the similarity measure, and B, to determine the value of K. The similarity measure is a mathematically calculated distance metric. And given a new case, K&N makes predictions based on the outcome of the K neighbors closest in distance to the point. Therefore, to make predictions with K and N, we need to define a metric for measuring the distance between the new case and the cases from the examples. In the previous video shows the two most popular distance metrics, which are the Euclidean and Manhattan. The Euclidean is simply this distance metric is simply the linear distance between 2 points in a dimensional space. And the Manhattan distance is a rectilinear distance. And what about the decision? The decision related to the value of K. This decision, the larger values of K, if we choose larger values of K, we reduce the effect of noise on the classification or regression. But also we make the boundaries between classes less distinct. More difficult to distinguish. And the best choice of K will depend upon the data we've got. An optimal value of K, to find the optimal value of K, we can use some heuristic techniques such as the cross-validation technique. And we cover this cross-validation, this technique, cross-validation, a couple of slides ago. You can pause the video here and go back to the slide about cross-validation if you want to refresh your memory. But cross-validation used for finding the best value of K in a KNN model works like that. First, we divide the set into n folds, and each fold has a training, a validation, and a test subsets. For each value of K we want to test, we need to train, validate, and test the model. The evaluations metrics value for each value of K that we are considering is then recorded. And here again, a metric could be, for instance, model's accuracy. Then we have to repeat steps 2 from 2 to 4 for all the folds of cross-validation with different random splits of the data into training and validation sets. The value of K that result in the best average performance metric across all cross-validation iterations is then selected. This is the best value for K we can get. You made it. You made to the end of this recorded lecture. You can pat yourself on the back and feel proud of yourself. I hope you have enjoyed this recorded lecture as much as I did, and I will see you soon. Bye for now.